Let's look at a function that's defined in terms of a power series. So we're going to let f of x be written in terms of a power series. So we're starting from n and going to infinity of c sub n x minus a to the n. The domain is going to be the interval of convergence for the series. So this guy is going to define a function, and as long as that radius of convergence is something other than 0, which means it converges not at the center only, but where the radius is greater than 0, or whether it's an infinite radius of convergence, then the function is going to be continuous, and we'll also be able to differentiate and integrate it. So what's kind of cool about this is that if we have a function f of x and it's written in terms of this power series, and let's say the interval of convergence is a minus r and a plus r. So just kind of reviewing what that means. Here's our center. We move r units to the right. That's where we're going to get to that right endpoint of the interval of convergence. We move r units to the left. Then we're going to get to that left endpoint. And I'm not worried about testing right now. I'm just going to use generically, not including the endpoints here. So if this is true for f of x, then if we were to take the first derivative, the interval of convergence, I'm going to abbreviate that, is actually going to be the same thing. It's going to have that same interval, a minus r to a plus r. And in fact, if we were to integrate f of x, and we're going back to that original here, integrating that series, then the interval of convergence would actually be the same thing. And that goes back to the idea that, those domains all have to match. If we were to take a derivative or integrate a function, we want it to match with the domain of f of x. So, and that domain in this case would be that interval of convergence. What can change, however, is the endpoints. So that endpoints convergence can change if we were to differentiate or integrate f of x. And we won't really know if it converges at the endpoints until we do our test at the endpoints, similar to what we did in the last problem. In the last problem, recall, we found the interval of convergence to go from 1 to 5, but we had to test what happened at 1 and what happened at 5 in that series to see whether or not it converged at 1 if it converged at 5. So we would have to do the same thing here. We would know the basics because we would probably know this, but we would have to determine what happens at the left and the right endpoint if we differentiated or integrated. So I want to kind of play with some of these ideas a little bit here. So let's say we have a power series that looks like this. Notice this guy is centered at 0, 0. What I want to do is just kind of get you used to the idea of differentiating these. Because remember, we're leading up to how do we solve a differential equation that's written in terms of a power series. That's where we're heading. So it would be nice if we know how to take the derivative. So let's do that. We can take the derivative term by term, and then ideally what we want to do is be able to rewrite that guy back into some kind of series. So let's expand this out just a little bit. If we plug in 0, then we would have c sub 0 x to the 0, which would just be 1. And 1 times c0 would be c0. The next term, if we plug in 1, would be c1x. If we substitute in 2, we're going to have c2x squared. If we substitute in 3, c3x cubed. And I'm just going to go one more. You want to have enough terms so you can see patterns. Rewriting things in terms of an infinite series, usually you're looking for what kind of patterns do I see from term to term, and then how can I write that concisely in terms of the summation notation. So we've got a few terms written out. Now let's take derivatives. So notice what happens with that first term. If I take the derivative of C naught, I'm going to get 0 because I'm taking the derivative of a constant, and the derivative of a constant is always going to be 0. So we're going to have a 0 there. If I take the derivative of the next term, I'm going to have a C1. The derivative of the next term, I bring the exponent down. I subtract 1 from the exponent. Next one, same thing. Bring the exponent down. Subtract 1 from the exponent. Bring the exponent down. Subtract 1 from the exponent. So adding 0 doesn't change anything in the problem. So we could actually think about not even putting that term there. So notice that we did lose a term from here to here, and we want to try to express this in terms of summation notation. An easy way to do this would probably be to start with that second term, just because there's more stuff in it. We have an x term here. We could view this as x to the 0 if we wanted to. I usually think it's just easier to start with something that has a little more meat than just a constant in it. So I want you to notice a couple of things here. Let me clean this up. So I'm going to start with this guy. This is my second term. So what do they have in common? They have a C1, a C2, a C3, a C4. So what if we start at n is 1? Then we're going to have a C to the n here. And that would give us our C in each case. Okay. Now, I also want you to notice that we are multiplying by some number here. So we could think about that C1 as a 1 times C1. So we need an n in here multiplied by that C. So if n is 1, we're going to have a 1C1. If n is 2, we're going to have a 2C2. If n is 3, we're going to have a 3C3, and so on. So that takes care of those constants. Now we just got to figure out how can we write that x term. So if we're starting with that second one, if we were to write this as n minus 1, would that satisfy what's happening with those exponents on the axis? Well, let's start with the first one. We want n to be 1. So if we were to plug a 1 in here, we're going to have x to the 1 minus 1, which would be x to the 0. If we were to move to this term, we would have x to the 2 minus 1, which would be x to the first. And if we were to check it with this one, we would have x to the 3 minus 1, which would be an x squared. So this seems to be working for all of our terms, which means that we can write this guy concisely this way. Now, let's think back to Calc 1 for a minute. When we took the derivative of a constant times x to some power, we said we kept the constant in front, we brought the exponent down, and we subtracted 1 from the exponent. So I want you to see the parallels between what we've done and what we did in Calc 1. So this guy really does look like this. It's just this is written in terms of a gazillion different sums, right? Gazillion different things added together. And a gazillion is not a real number. But if we were to take the derivative of this guy, this would just be one term. It would look like this. Look what happens when we took the derivative of this. When we took the derivative of that, it really does look the same way. Notice that the index did change here. The reason we changed that index is because we lost a term. Now, we could, and we'll talk about this in a few minutes, but we could change this and tweak this. So instead of starting with n as 1, we could start with n as 0 or n as 2. We could change that index. And like I said, in a few minutes, we'll talk about how that change of moving that index will affect what happens inside of that summation. Now, let's continue with this. What if we want to take a second derivative? Second derivatives kind of work the same way. We're going to take the derivative piecewise. So if I take the derivative of that first piece or that first term, the derivative of a constant is going to go to 0. If I take the derivative of the second term, I'm going to have a 2c2. If I take the derivative of the third term, so I would have a 3 there. I would bring the exponent down, and then I would subtract 1 from the exponent. We could also write that as 6, but if I leave it in terms of what's multiplied together, it may make it easier to come up with that formula at the very end. And then that next one, we're going to keep the 4 and the C4. We're going to bring the exponent down. We're going to subtract 1 from the exponent. So there's a few terms that's written for that second derivative. Now, adding 0 is not going to change the problem, so I'm just going to scratch that out because we really don't need that guy. So let's rewrite this. We want to write this as easily as we can. So what do these terms have in common? That's what we're looking for. Well, they definitely have a c in common. So it's going to be c to the n. And if we start at 2 and go to infinity, it would be really easy to get that c2, that c3, that c4. So this would start at 2. This would start at 3. And this guy would be at 4. So we're looking for those patterns again. I'm going to write this over here. I think it's going to be easier to identify things here. So we have our Cn. So if n is 3, we would have a C3 there. Let's think about how we would get that number here and that number here. To get that 3, if n is 3, we could just use n. To get to the 2 from 3, we would have to subtract 1. So n minus 1 there. So does this give us those coefficients there? Let's check it. If we were to substitute our n in, and keep in mind our n is 3 because we're dealing with that second term. It's just got more meat to it than that first term does. So if we're looking here and we're using 3, we would have a 3 times a 2 times a C3. Is that what we have here? And since it is, we're good. So now, how do we write that term? Well, our exponent's 1. If we're going to start at 3, how do we get to a 1? Well, we could take our n and we could subtract 2 there. So let's try it out. If we take a 3 and we plug it in here, 3 minus 2, that gives us that exponent of 1. Now, let's take this guy and let's test it with that first term. If we were to substitute those in, would we get this guy back? Let's plug in that 2. So we would have a 2 times a 1 times a C2, x to the 0. 2 times 1 is 2. So we would have a 2c2, x to the 0, and we know x to the 0 is 1. So it does give us that term back. Now let's check it with this guy. So if we plug in n is 4, so we would have 4 times 3 times c4, x squared. And that does give us that back. Coming up with this is really about looking at what you have and looking for patterns. Now, let's go back to Calc 1. We found the first derivative and we got this. What if we wanted to take the derivative of what we just had? Well, if you think back to Calc 1, to take this derivative, we would keep those constants in front, so Cn. We would bring the exponent down, and then we would subtract 1 from the exponent. So we would end up with that guy. And you can see the parallel between what we would have done in Calc 1 and then our second derivative here. They look really, really similar, if not identical, minus the summation notation there. So sometimes starting with a power series, if it's a nice power series like this one, we could take derivatives just using those basic derivative rules that we established back in Calc 1. So we actually could go from here to here. But notice what did happen to the index. The index did change because we lost a term when we took that derivative here, because the derivative of that first term was a 0. And we lost another term when we took the derivative from here to here, because the derivative of that first term was 0. Which means the second derivative of the original would also be 0. So you can see how that index moves a little bit based on how we're taking derivatives. So I want to talk about just 2 more quick things: the identity property and being analytic at a point. This guy is a definition, this guy is a property. So we'll start with the property. It says if we have a sum, we're going from 0 to infinity, of c sub n x minus a to the n. And we want that to add up to 0. So we're adding a whole bunch of terms together, and we're going to get that sum to be 0. But the radius of convergence is greater than 0, which means it's not converging just at the center, it's converging for other x values. So the only way that can happen is if this guy ends up being 0 for all of our n values. So we want to just kind of recap. We want to add a whole bunch of things. We want it to go to 0 when we add all these things. But the radius of convergence is something other than 0. So we have a pretty wide range of convergence here. It's not converging just at this value. It's converging on some interval here. And it could even be an infinite convergence. It just has to be something other than 0. So it's converging on some interval. Then the only way that I'm going to add a whole bunch of terms in here, if I plug in something other than a, the only way I'm going to add a whole bunch of terms and get 0 is if I'm multiplying all these terms by 0 to begin with. So that's what the identity property says. And then analytic at a point. This guy is a definition. So we have a function f is said to be analytic at a point A if it can be represented by a power series in x minus a with either a positive or an infinite radius of convergence.